All right, for today, this chapter, this section, I should say, is actually, I think, a little bit easier than some of the ones we've had, so hopefully it'll give you a little time to catch up. Um, we're talking about absolute maximum and minimum. So remember, we've been finding local max and mins by finding our derivative, setting it equal to zero, seeing if it's increasing, decreasing, etc. We're just going to add to that a little bit. When they say absolute, what that's saying is what is the highest point or the lowest point. So I'll show you kind of a quick example of what I'm talking about, the difference between the local maximums and the absolute maximums. So give me a second away from this here, just kind of show you what I mean. If you have a graph that looks like this, okay, we know that this is a local max, and this right here is a local min. We've spent a lot of time figuring out how to get each of those points exactly, okay? So give you another case here. Let's say we got one going down like this. Again, we got a minimum, we have a couple of maximums. What we have here is this is still a local min, this is still a local max. This one on the top here is still also a local max, but it's also at the absolute max. Because you see how in the entire picture it is the highest point. It's like a bunch of mountaintops are local maximums, but what's the highest mountain? That's what's known as the absolute maximum, the highest around. So if you look at this one on the left, there's no absolutes. No absolute maximum because this graph just keeps going upward. No absolute minimum because it keeps going downward. So even though this is a high point right here, there are higher points here, here, here. There never is a maximum. Whereas on this graph on the right, that's your highest point and no other point gets higher than that. This one has no absolute minimum. So that's really all it is. That's what this whole section is talking about, is this idea of the absolutes. Okay, so kind of add to that here before I go back to the slides. You're going to be finding, those absolute maxes and mins, wherever they are on your picture. And the idea is that sometimes you don't have the picture. So I may have a graph that looks like this, but what they're going to say is, we want to know between here, they're going to give you a domain or an interval, and they're going to say, okay, in this interval, what's the absolute max and the min? So that's the part they're looking at. It's just right there. They don't care about the rest of the picture. So just looking at this one, by eyeballing it, I can see this is the absolute max, and this point way down here is the absolute min. So the summary is going to be that it's either going to be a local max, if we're looking for the absolute maximum, it's going to be go find all the local maximums, like here we have one. It's either this or it's going to be one of your endpoints. For the minimum, again, look at the local minimums. It's either this or it's going to be one of your endpoints. And that's what we have to check. We want to see which has the highest or lowest y value when we're looking at these absolute max and min. So the technique isn't always shown here in some of these beginning problems. That's why I wanted to go over this here. But this is what's going on. This is all we're going to be doing this chapter. We're going to learn a couple of theorems, but they're not going to be anything too extreme, too outrageous that we have to worry about. Okay, so I'll get into this and show you what I'm talking about. All right, so they're going to give some technical definitions, and this is going to matter when you look at the homework. You might want to make sure you understand what this is all saying. So it's a local maximum, which we've already dealt with, is saying that all the x's are going to be less, all the y values are going to be less than this given maximum for all the values nearby. Okay, so what that's getting at is, here we have a local maximum right here. This y value is f of c, given that that is the c that we're looking at right here. They're saying all the other y values nearby are going to be smaller than it. That's the definition of a local maximum. It's just that in the immediate area, it's the highest of all the other y values. Okay? So that's all that's going on here when you talk about the local. So that's your little review. Now we're going to talk about what it means to be an absolute maximum minimum. And you see here, for a certain given point, it's going to be bigger than every single y value, f of x. Okay, so this y value right here is bigger than all in the domain. Okay, so whatever you have, depending on what your domain is, if it's the highest, it's kind of like if I was able to, but we have a continuous graph, so it goes on forever. But if I was able to list every single coordinate and line up my y values and sort them out, whoever's on the top, that point is going to be the absolute maximum, the highest point ever. Like I said, like the highest point on Earth. We have a bunch of mountains on Earth that have high points, but out of all those high points, what's the highest mountaintop? That's going to be the absolute maximum. Same thing with the absolute minimum here. Okay, so they use that phrase again, the absolute extrema or extremum. It's just the extreme points that we have. So we'll get to a graph right here, and you can see here we're looking for absolute maxes and mins. Well, there's definitely a high point, a local maximum right here. But is it the highest point of the entire graph? Well, no, because the graph just keeps going up here. So if you have a graph that goes up all the way to infinity and never comes down, that means you have no absolute maximum. Okay? Same thing with the minimum. Here's a local minimum down here, but because the graph keeps going on forever, it's not the lowest point out there. So therefore, you're not going to have, say we have the two local mins and maxes, therefore we're going to have no absolute minimum is what I was trying to say. They don't have that on here, but you can see here, this part is talking about this local. So just get the difference between there's a local maximum and there's absolute maximum, maybe that, but in this case, again, there's neither. No maxes, no absolute maxes, no absolute minimums. Now we do the same thing here. We have to consider every local maximum. Again, it's like looking at every mountaintop. Let's see, if I want to find the highest point on Earth, let's start with all the tops of the mountains and see which of those like the best of the best. So the absolute extremum here, we're going to find all these, we're going to look for these. I look for a local maximum right there, and look at the rest of the graph. Nothing is higher than that. That is going to be my absolute minimum as well. Okay? Now for minimum, or maximum, hope I said maximum. Minimums, there's no local minimums. There's also no absolute minimum because this graph just keeps going downward. If it goes up or down forever, if it goes up forever, there's no absolute maximum. If it goes down forever, there's no absolute minimum. So that's the deal here on this one. And notice the key is everything's going to be revolving around the derivatives and the locals. That's going to help us decide what we have. Okay, now another weird picture here. This is one of these, if you remember, it's not a smooth graph. It's kind of pointed down there. It's one, though, that if you would find the derivative and you check it, you'd see that it is a local minimum. This graph has no local max because it goes on forever. It does have that local minimum right here. And that local minimum is also going to be the absolute minimum because it's, again, the lowest point on the entire graph. Just think, the whole picture is what I mean when I say absolute. Okay, so we have a theorem here, and the good news is you're not going to have to memorize these theorems, but you're going to have to know how to put them into action, know how to work with them. Okay, so in this case here, we have a function that's continuous. Remember, continuous means there's no gaps, no breaks, no vertical asymptotes. So if you have a closed interval, a to b, and it doesn't matter what a and b are, we're going to go between this point and this point, there's going to be an absolute max and an absolute minimum. The only time we don't have absolute maxes or mins is when our graph goes on forever, but since we're closing it off in this interval, there's going to be a point where the graph is going to stop, and then we can see what the max and min are. So go with an example here. We have a cube function. F of x equals x cubed minus 21x squared plus 135x minus 170. We want to know what's the absolute extrema on the closed interval 2, 12. Now remember, these are x values. The lowest x value is 2, the highest x value is 12. Normally this thing is going to be a domain of all real numbers, but they're going to close it off. And so they want to know for just these points between 2 and 12, what's the absolute max, what's the absolute minimum. So here's the picture. Okay, remember, it's a cube function, so it does go on forever, but they're stopping us at 2 to 12. So this is it. This is all we have to look for here. All right? So how do they know it's an absolute max? Well, we can look at the picture and see what's going on here, but what we're going to do, our process is going to be soon, we're going to find still the local max and mins. What are the critical points, okay, in between? What are those partition points? And we're going to see, are any of these local maxes or mins? If there's a local max, like this one is right here, we're going to check it and see what its y value is. Okay, it's 100 something. Then we're going to compare it to the endpoints. Let's take the y value at 2. So remember how we're getting these. We plug 2 into the graph. We get a 24. Then the other end, 12. Plug 12 into the graph. We get 154. We want to see what's the highest of all of those, and that's your absolute maximum. And then you do the same thing for the minimum. Let's find all the local minimums that occur between 2 and 12. Let's check that y value, compare it to the endpoints, and see whatever the lowest is, and that's the absolute minimum. So in this case, if you know how the graph looked, but we're going to pretend that we don't have the picture. We're going to do this all on paper, all with our techniques here. So I would go and find the y value of the two endpoints. Plug in 2 and 12 to this function. That's your ends. Now look at any max and mins, local maxes and mins in between. See if any of them exceed, because it's possible this graph could have gone way up here and then down. So neither of the endpoints would be the maximum. It would be that local maximum. Same with the minimum. It could have dipped way down here, but you won't know until you plug them all in. There's no rule that says it has to be this or that. So plug in the endpoints, plug in the local max and mins, and see what you get. Okay, same thing on this picture. Now we're going from 4 to 10, same graph, but look at where it is. We're only taking the points between 4 and 10, so it's the same process. I have a local maximum right here at x equals 5. It has a y value of 105. When I plug in 4, doesn't show it, but when you plug in 4 into this picture, you're going to get a not much, but a little smaller y value. Same thing when you plug in 10, you're going to get a smaller. So of the three, the two ends and the local max, whoever's the highest, 105, that is going to be your absolute maximum. And the same thing with the minimum. Plug in local minimum here at 9, plug in 9 to the function. 9 gives you a y value of 73. Compared to these are the two y values. That's the lowest, that's the absolute minimum. Okay, so as you start changing the domain, it's the same picture, but we're going to go on different intervals. Just look, the whole point of these slides is to show you the visual of it. Okay, if I'm looking at this little group right here, the absolute maximum is right here. The minimum is, again, the lowest of all the points. Well, here's the endpoint, here's the endpoint. This is the minimum, absolute minimum. Okay, so look that over for a second. Make sure you're understanding it's again, just by out of the entire picture, what's the highest and what's the lowest. Okay, now we change the interval again. We're going from 3 to 11. Notice these points happen to have the same height, the end right there. So the absolute maximum, they're both at 105. So when you say it, it's going to be both at 5, 105 and 11, 105. But if they're asking what are the x values, if there's a tie, they're both the winners. Okay, just again, go back to my example of the highest point on Earth. Let's just say two mountains both had exactly the same highest value, highest elevation. Then they would both be considered a tie. They'd both be considered the absolute maxes. Just like over here, the absolute mins might be two different points, so you list them both as the absolute minimums. Okay, so again, another theorem here. This is what I've kind of been saying already. If they exist, okay, they must occur at critical numbers or endpoints. All right, now the other part they didn't say is making sure it's continuous. Okay, so to see if it's continuous, pretty much everything we've dealt with so far is continuous. The only thing we got to worry about is if inside of that function there's a gap, there's a vertical asymptote, there's a place in the domain that doesn't exist. That's what we worry about by not being continuous. So still one of our first steps is we need to check the domain, make sure it's good. So if it's a polynomial with high powers, you're going to be fine. You don't have to do anything. You know it's going to be continuous. But if you have a square root function, or especially if you have an x in a denominator, you have to worry about a gap, a hole, a vertical asymptote, and that will render this theorem not exactly true. We got to check some more stuff. It's really what it's going to come out to be. So find the critical numbers. Remember how we find the critical numbers. Every place that is going to be derivative equal, the derivative is equal to 0. Find the derivative, set it to 0, solve for x. Those are my critical values. So they evaluate f. Now when they say evaluate f at the endpoints, they're basically saying plug in the endpoints to the original function. Go find the y values. So whoever's the biggest of all of those is going to be, it's not just the largest values. Oh yeah, sorry. And the critical values. You're going to check all of the critical values, plug those into the function, plug the endpoints, and then whoever's the biggest number, biggest y value is the absolute max. Whoever's the smallest y value is the absolute min. Okay, so let's see a little more in action here. So we have a polynomial right here, a cube function on the interval -7 to 7. So number one, it's going to be a continuous function. Okay, the reason we know it's continuous is because there are no gaps in the domain. There's no problems in the domain. The normal domain would be all real numbers. That means every point exists. So we have a nice continuous graph. So first step, find the derivative. Okay, the derivative isn't so bad, 3x squared minus 12x. And they've already factored it, but that's in preparation of setting this thing equal to 0. 0 equals 3x squared minus 12x, so 0 equals 3x times x minus 4. Set the whole thing equal to 0, you get x is 0 and x is 4. Those are my critical values. Now, at this point, just kind of make sure your critical values, you only care about the ones inside the interval. Okay? So 0 is in between -7 and 7. 4 is in between -7 and 7. Therefore, we're okay. They're both good. Now, let's just say, for example, this was a 14. If it's outside of there, you just ignore it. You don't care about any critical values outside of this because this is all you're testing. This is all you care about between -7 and 7. Okay, so my critical values are 0 and 4. We have endpoints -7 and 7. So remember, the next step is we plug all 4 of those points into the original function. So we're evaluating the function at the endpoints and at the critical values. What's f of -7? What's f of 0? What's f of 4 and what's f of 7? Not in the derivative, but in the original function because we're looking for y values. So, that was backwards right there. Yeah, this is a typo. Let me just see if I can, let me fix that. Sorry about that. It's supposed to be f of -7 equals -1, I believe. Yes. Okay. So let's bring that back up. And like I said a couple times, every now and then you're going to get a PowerPoint that's got a little error from the publisher. They make mistakes. Not a big deal. Okay, so f of -7, pretend there's a parenthesis there, equals -1. F of 0 is 0. F of 4 is -32. And remember, for all these, they're plugging these values into the original function. So if all of our values up there, our critical values and our endpoints, we look at who's the highest point. It's 49, therefore, when x equals 7, that's an absolute maximum. The lowest point is -32, so when x is 4, that's your smallest, that's your absolute minimum right there. Okay? So, just kind of summing up what we found here. Absolute maximum at x equals 7, absolute minimum is x equals 4. And make sure you answer the question. Sometimes they're going to ask you, where is the absolute maximum? You say x equals 7. Sometimes they're going to say, what is the absolute maximum? Then you say the highest is 49. So make sure you know what the question is on there. Okay, so a couple other things here. We have f prime of c, some value. We've done this before. If your derivative equals 0, then you know there's going to be a critical value here at c. Okay? Now, what we were doing before is we would check and see, well, is it increasing or decreasing to the left and the right of that point? So if it's decreasing, then you hit the C, then it's increasing, you know it's a local minimum. Another test we can try, I don't know if this is better or worse, but instead of testing regions, we can go find the second derivative right here at this critical value C. So if you know we have a special point, a C value, let's say it's a critical value at x equals 5. Well, instead of checking to the right and left, you can take that 5 and plug it into the second derivative, because remember that tells you concavity. If you know if it's positive, then it's concave up right there. That means this point must be a minimum. On the other hand, if you plug that into the second derivative and it's negative, that means it's concave down. That has to be a maximum. So it's just another way to find what if it's a local max or min is. You can test it in the second derivative. So that's what this second derivative test is all about. Okay, so now critical number where the derivative of that point equals 0. So the second derivative is greater than 0, then it's a minimum. If the second derivative at that point is less than 0, then it's going to be a maximum. And that's all we're talking about right here. You look at these things here, they just tell you if you actually get the first, you plug in an x value in the first derivative, it's 0, and it's also 0 in the second. Remember what that means is second derivative of 0 means it's an inflection point. So if you have a value and it's possibly a local max or min, but it's an inflection point, that means it's going to be kind of hard to tell what's going on. You may not get a conclusion, and that's what they're saying is the test doesn't apply. It's only when you get a positive or negative number in the second that you know what's going on. You know it's a min or a max. And remember, it's the opposite. When you see the second derivative positive, that means you had a minimum. It's the bottom of a concave up graph. If the second derivative is negative, then it's the opposite. It's a local maximum here. Okay? So that's your second derivative test. And again, this is just kind of a rewrite of what we have going on here. Nothing new. You can kind of read that over if you need. Pause it if you're not sure. Okay, and then the last one, we'll do another example here. Find the absolute extrema on the function of this graph right here. Okay, between 0 and infinity. Now notice, not including 0, obviously you never include infinity. So this is going to be an interesting thing here as well. Okay, so let's see what we get. We have a solution for the derivative. Okay, so make sure you see how we get this. This 4 over x is like 4x to the negative 1. So when you take the derivative, you get a negative 4x to the negative 2. The derivative of x is 1. So now they took this and they cleaned it up. They made a common denominator, and then they factored it in preparation for the next step. Let's plug in 0 right here, and then we get critical values of 2 and negative 2. Okay, so remember, as I said earlier, we're only looking at the interval that's positive. So we don't care about this negative 2. We only care about that one. So something special may be happening right here at x equals 2. So let's see what happens when we plug in the second derivative. So I take this second derivative, I get 8 over x cubed, plug in this 2 right here, and so we already, as what I just said a minute ago, the only critical number is 2. We plug in 2 to the second derivative, and it's a value of 1. What we care about is it's positive. Therefore, at 2, it's a concave up. Therefore, we get a minimum right there at f of 2. Okay. Now, I would take this a step further and graph this a little more just to see what's happening around that 0. Because you remember what I was saying to do before is you plug in the endpoints. Well, there are no endpoints. You can't plug in infinity, and you also can't plug in 0 because 0 doesn't exist. So we're looking at the points right by 0. So we want to make sure that is there a maximum? Is there an actual minimum? Because there's a couple ways this graph could go. I'll show you what I mean. Okay, so we know that there's a local minimum at 2. But we don't know what that looks like. Sorry, I'm trying to draw. Okay, sorry, trying to get the pen working here. So, show you what I'm talking about, a couple scenarios here. We know there's a local minimum at 2. Okay, now does that mean my graph looks like this? We know we can't have a 0, possibly. Okay, but I'll show you another case here. It's possible at 2, you could have a graph that looks like this, for example. Okay, now I'll tell you why you can't have that is because if you did, you would have had another extrema right here, but we said there's only one. So this top graph is most likely the picture, but I want us to kind of have an idea what's going on here. In doing that, I just want to confirm what happens as we approach 0 from the right of the function, and also what happens as we approach infinity of the function. Okay, now I'm bringing this up now, and you'll see we don't have to do this every time because of what I just stated, where there's no way it can turn around, in the middle of that function. But I want to never assume that until you guys really understand what's going on here. So let's look at our function. Remember what it was? This one, this f of x equals x plus 4 over x. So I want to find the limit as x approaches 0 from the right side of x plus 4 over x. Okay, so think about what's going on here. We're plugging in very small numbers. That thing is becoming a 0. This thing is being either a positive or a negative infinity. Well, how do we know? Let's just plug in something like 0.001. That gives us 0.001 plus 4 over 0.001. Tiny number on the left, big number here. I think it's like 400. The point is, it's positive. Just kind of confirms this thing is going to positive infinity. And if it was going down to negative infinity, like I was theorizing it could have been over here, then this would not be my absolute minimum. There would be no absolute minimum. So it's definitely going upward. What that confirms is, like this over here, there is no absolute max. Anytime you have the graph going up to positive infinity, there's no absolute max. Last thing I want to check, though, is let's just make sure as we go to infinity, we're okay as well. So here's my function. As we go to infinity, remember that thing becomes 0. That thing becomes positive infinity. Therefore, this side is also going to positive infinity. Just sort of confirmed what we pretty much knew, but I want you to always, don't be afraid to come up with that if you need to. If you need to show that, if you need to work that out, don't be afraid to go plug in a number close to 0. Plug in a number over far to the right just to see what you get there. Okay, and one last time I'll show you the picture here. We have x plus 4 over x. Okay, and I'll zoom out a little bit. We're only looking at this side, but this shows what we found. Remember, it's going up to infinity from the right side, and the other infinity is going up here, confirming that was an absolute minimum. This happens to be the other side of the graph, but the problem we were looking at only cared about, where'd it go? It only cared about the points 0 to infinity. So this sort of confirms what we knew, and that's the graph that we have there. Okay, so let's look at a couple homework problems. And like I said, that's it for this section. There's not a ton of new stuff. Just got to make sure you know how to find all these points, know how to come up with these absolute max and mins. We're just like many sections, we're just adding a new layer, a new step to the process here. Okay, so let's look at our assignment here. And you see, I'm trying to make the homeworks open up in case you want to go ahead. I've already got homework number 13 for the week after, which is after spring break. So that's why I didn't make that as tough. So let's just do a handful of these to make sure we're all in 100% agreement with what's going on, what these problems are all about. So let's just do number 3. And then a couple more. Okay, so we have the graph shown to the right. we want to find the absolute minimum and absolute maximum on the interval from 0 to 10. All right, so there's no equation here. Just look, it's all by the graph. So don't be afraid to, there's this button here. There's the magnifying. It doesn't make it that much bigger, but this one opens it in a new window, and this really lets you see it a little more up close. So the points that we care about here are the local maxes, which is this one right here, local min right there, the endpoints at 10 and x equals 0. Those are what we look at. So out of all those, we're looking at what's the highest. Well, that's the highest right there. This is going to be my absolute max. And then what's the lowest? That's the lowest right there. So that's going to be my absolute minimum. Okay? So to answer the question here, we want to see from that, and you can see it's 1, 2, 3, 4, 5. It looks like it's at 2. So here's what I wanted you to see here. The absolute minimum, the y value, is at 2. So when they say what's the absolute minimum, they want to know the number. Where is it at? It's at x equals 0. Okay? The absolute, yeah, so that's the absolute, oh yeah, and I'm going to pick this one because if there's more than one way we do that, there's only one, so we're picking this one right here. And there's our first answer. Okay? Absolute maximum we saw was that looks like it's at 10, 10. The y value, just think, when they ask for the absolute maximum, they want to know the y value. When they say x equals, where is it at? Oh, once again, there's only one, sorry. So do that one, and do this one, and there's that. And that's all they wanted on this problem. That's all that we're trying to find on number 3. Okay? So let's look at number 7. Okay, similar type of question. Find the absolute max and the absolute min on the graph to the right. So, kind of illustrating my points, I got a point in here, I got a point in here, here, and here. And I'll tell you, oh, I'm sorry, go back. They want to know between 1 and 5. That's the question that we're looking at. So let me pull up the picture. The only place we're looking is between 1 and 5. So that's going to be between here and here. So look at the endpoint, look at the endpoint, and look at any local max and mins in between, and that's how we're going to get our answer. All right, so you see, we ignore this because it's not in the domain that's given, and we ignore this. We're only looking at the graph right here between 1 and 5. So from that, I can see here is my absolute max, and the coordinate looks like it's 3, 5. And then out of all of them, this looks like my absolute min, and that coordinate looks like it's 1, 3. Okay, that's my absolute minimum out of the graph we're looking at. This is the lowest point ever. This is the highest point ever. This other endpoint has nothing to do with it. It's right in the middle. We ignore that one. Okay, so now the absolute max is a y value of 5, and it's at x equals 3. Did I count that wrong? Pull that picture up again. Make sure I got that right. Oh, minimum is what they asked. I'm sorry. Go back. Minimum is the first question. That was at 1. Is it 1, 3? Yeah. 1, 3 is what we had. So the y value is 3. The x is 1. See the point down here. What is the absolute minimum? It's 3. Where is it at? It's at x equals 1. So now we have that. Now I go to absolute maximum. At the point 3, 5, so the absolute maximum is 5. What's the highest elevation we ever get? It's 5. Where is it? It's at 3. And there's the answer to that question. Okay? Hopefully that part is clear to everybody. If you're not sure, feel free to shoot me an email and I can talk to you a little more in depth about that. So let's look at number 11. Okay, so now they're not given the graph, they're given the equation. We want to know what's the absolute max and min over these two intervals. So let's start with this one. First step, remember, is let's make sure it's continuous. And you don't have to write anything for that. You just have to look. I look at that. I know the domain is all real numbers. I know there are no problem points for x. Therefore, it's continuous. Now I jump right into the derivative. And I get a 4x and nothing else. So we set that equal to 0, and we solve for the x. We get a critical value right here. Okay, so for my first interval, we're going between 5 and 7. Okay, now you look at this right here. This is not in between 5 and 7. So for now, we're not even looking at it. For the first part of this problem, all I want to find is f of 5, f of 7, and I have nothing else. And those will be my maxes or mins, whatever they might be. Okay? So when I plug into that original equation, and I'll say that again, the original equation, we're plugging in 5 right to here. Okay, so let me go kind of off to the side here. F of 5 gives me, looks like it's 50 plus 3, so we get a 53. F of 7 gives me 2 times 49, which is 98 plus 3. That's a 101. So what that tells me is, because there are no maxes and mins inside of the interval 5 to 7, there is no turning around. These endpoints are my absolute maxes and mins. The absolute max has a value of 101, and it's at x equals 7. The absolute minimum has a y value of 53, and it comes at x equals 5. That's it for that first two parts. Okay, so now, I know, oh, there's part B. Okay, so they're not always clear here. This is part A, these first two, these are part B. So we do the problem again. Now here's the good news. For the next interval, I'm going from -7 to 7. So I still look for my critical value. This time, the critical value is inside my interval, so I have to account for that. I need to go find the endpoints, so no longer 5. That's not one of my endpoints. -7 is an endpoint, 7 is an endpoint, and also I need to find 0. Those are all the things I need to find. Okay, so I've already done the 7 on the right, so I'm going to leave that there, but I need to find -7 now. And you'll notice this isn't going to be too bad. -7, I'm still squaring it. I'm still getting 49 times 2, which is 98 plus 3. I'm still getting a 101. Okay, that's an interesting idea. We'll see what happens in a second. When I plug in 0, I get a 0 plus 3, I get a 3. So what that tells me, my conclusion is, this is an absolute max, but also this one is an absolute max. And this one is an absolute minimum. We're only looking at the y values to tell us the answers. Okay, so if I was to graph this, I would tell you what's really happening is we have a 0.03, we have a 0.7101, which is way over here. We have another -7101 on the interval. It looks like we just have a parabola, and that's what this is right here. That's why this is the absolute min, and both of these other ones are tied for the absolute max. Okay, so my absolute maximum is 101, and it's happening at -7 and also at 7. That's that comma between the x's. Remember, we're listing x values here, 7 and -7. My minimum is 3, and it's at 0, and that's it for this problem. Okay? Any questions here? Let me know. Hopefully that makes sense to you all. All right, so let's look at another one for you all. This was number 11. So let's go on to number 15. Okay, find the absolute max or min if it exists. Now they're not giving us a domain, they're just saying on the entire function. Okay, so here's my function right here. First step, is it continuous? Well, no problem with the domain, no missing x's, no bad x's, so therefore it's continuous. So I'll go right into the derivative. Set that derivative equal to 0, and you get a critical value of 7. Okay? So that could be a local max, it could be a local min. Don't know, but here's what I'll do. I'm going to find the second derivative. Notice the second derivative is just 2, and there's no x there, which means this thing is going to be concave up the whole time, everywhere. And remember, we know this is a parabola. That makes sense. It's a concave up graph. This should be the low spot. So when I plug that into the function, I get 49 minus, I think that's a 98, plus 1. So I think I'm getting negative 49 plus 1, which is negative 48. That right there is going to be my absolute minimum. All right, the minimum is negative 48. It's occurring at the value of 7. And now for the maximum, I know because it's a parabola and it's concave up everywhere, there is not going to be a maximum. But if you're not sure, remember what I've been showing you is let's plug in the endpoints. Well, there are no endpoints to plug in. What we really want to know is what's happening as this thing goes to infinity, and what happens as you go to negative infinity. All right, so first off, because it's concave up everywhere, it shouldn't be turning back downward, because if it was to turn downward, you'd see a concave down section here. So this thing should go all the way up to infinity. If you're not sure, take that function and just watch what happens when you go to infinity. This x squared just means a big infinity. It kind of confirms this thing is going to infinity. That's how I know there's no absolute maximum. Okay, and that's all there is. Sometimes you got to trust your instincts and what you know about the picture, especially if it's a graph you already know. Don't worry about trying to prove it. If you know this thing's going up to infinity, there's no minimum, or sorry, no maximums there. Okay, so let's look at number 19. Find the absolute max or min. Now this is of the same graph, same example we kind of had on the PowerPoint. Let me actually pick another one since you've kind of already seen this one. Let me see if there's one close to it. So you can get a different taste of what's going on. Well, it looks like they're going to use that same one a couple times, so let's just do this one. So we want to know what's the absolute max and min. First step, as you've heard me asking every time, is let's make sure it's continuous. Well, wait, we have a problem. We don't have anything at 0. So continuity is going to be a problem at 0. That means something may be going up or down to infinity. So let's just go and keep that in the back of our heads because we have to know what happens there. But let's go find the derivative. Now first, let me rewrite the equation. Not the derivative yet. This is still the original equation. And this might clarify what we went over in the PowerPoint earlier because they didn't really explain everything or show you exactly what happened here. So here's my first derivative. It is negative 4 over x squared. 1 minus 4 over x squared. Now, as I set this thing equal to 0, there's a couple ways you can do this. You can make a common denominator, and you can set the top equal to 0, or you can just multiply everybody by x squared, and you get this. Therefore, I'm going to get x equals negative 2, x equals positive 2. These are my critical values. They're in the domain, and they're places where your derivative is equal to 0. Okay? So, we can find those, and we can tell what's going on. We can get the actual y values of those. So let's do that for a second. Let's find f of negative 2. You get negative 2 minus 2, so you get a negative 4. let's find f of 2. You get 2 plus 2, you get a 4. So here are some special points. 2, 4, negative 2, negative 4. I don't know if those are maxes or mins, local maxes, local mins. It's not always easy to tell, so we have to go figure something else out. Now remember, I'll go try this technique here. Let's look at our second derivative. This is again kind of what you saw earlier. All right, I'm going to take this and I'm going to use that to find the second. You guys see why I'm doing that is I could take this one, but the problem is it's got that fraction. I have to move that power back up anyway to the x negative 2, so I'm just going to take that one. That's an easier derivative to find. We get 8x to the negative 3, and if you recall, this is how they got this 8 over x cubed. Okay, so what I find is if I set that equal to 0, I have no inflection points. I don't care about inflection points. I want to know what happens when I plug those two in. What happens when I plug in 2 to the second derivative? What happens when I plug in negative 2 to the second derivative? And sure enough, that becomes a positive number. That becomes a negative number. So what I know is when you plug in 2, you get a concave up graph. That means this is a local minimum. And this is a local max. Remember, because it's concavity, if you have a concave up graph, that means this point is at the bottom of it. Here you have a concave down, which means this point is at the top of it. Okay? So now the question is, this is a local max right here. Is it the absolute max? Well, think about it. Absolute means it's got the highest y value. So it's either going to be a local max or it's going to be some other point. But look at this one. Local max has a negative 4. This one already has a higher y value, and it's the minimum of its graph, which means there's a bunch of other high y values. So therefore, there is not going to be an absolute maximum. Okay? You can't say it's at negative 4 because here's proof there's already a higher y value. And like I said, because this is at the bottom of a concave up part of a graph, there's a ton of points higher than that. So no absolute maximum. And when you go to part B, same kind of thing. Here's a local minimum at 4, but here's a point smaller than 4, and there's a bunch smaller than it. Therefore, there's no local minimums. Now, if you're not sure, the other way to go. Okay, I'm going to erase this, and then I'm going to show you the graph, which you don't always have that ability to graph it, because this is supposed to help you graph it, but show you this. We know there's trouble at 0, okay, because remember the graph doesn't exist at 0. We knew there was a local minimum. What was it at? 2, 4 was a local min. And at negative 2, negative 4, we had a local max. Okay, what we don't know is what happens here when you go to infinity and negative infinity, and what happens as you get close to that 0, that point that doesn't exist. So I'm not asking you to do this every time, but here are the questions you want to ask yourself. What happens as you go to positive infinity? What happens as you go to negative infinity? That takes care of these two halves of our graph here. What happens over here? Then you want to know what happens as you approach 0 from the left, and what happens as you approach 0 from the right. Now, like I said, this is sort of the extreme extra that you don't have to do, but I just want you to get an idea of what happens. So you can go take this function right here and start plugging in numbers. Well, I already talked about this before. When you go to infinity, this graph is clearly going up to positive infinity. That's enough to tell me no local max. When you go to negative infinity, this graph is going to negative infinity because of that first x. That tells me no local min. And if you went a step further, you'd see as you go to 0, it's going up here, and as you go from the left, it's going down here. That's how you know there's none, no local max, no local min. You only have to find one extreme to kill it. Okay, now my last part, like I said, I just wanted to show you quickly how that graph looks. We already graphed this, but don't be afraid to go back into Desmos, and you see this is the one we found. 2, 4 is a local min, but it's not even close to the absolute min because the graph goes so far. Same with -2, -4 being an absolute max. All these points are higher. And if anything goes to infinity, that's it. No local max for that part, no local min if it goes down to -infinity. Okay, so let's see if we've got something for 23. I think it's still in section 4.5. Yeah. Okay, so same thing on this one. We want to know what happens to our graph. Do we have an absolute max? Is all they're looking for. So here's my function. And we're only looking for a max, and we're only looking on this side of the equation. Okay, now notice, I already know right here, I cannot have x equals 0. There's a problem there. Okay, now that's not in my domain anyway, but I want to know what happens as you get close to 0. I want to know what happens as you get close to 0, as you go toward infinity. And mainly I want to see, are there any critical values in the middle of that? So first off, let's rewrite that original function, and now I'm going to find the derivative of that. Sorry, first derivative, not second derivative. So we get a -16 plus 16x to the -2. So my first derivative is -16 plus 16 over x squared. And to find our critical values, we still set that whole thing equal to 0. And we get 0 equals -16 plus 16 over x squared. And as I did for that last problem, my simple way is I just come along and multiply every side, every term by x squared. So let's say we multiply this by x squared, we multiply all this by x squared, and that's how you get the next line. You get a 0, you get a -16x squared, and you get a 16. So I'll move it over to this side, and then it's just back to our favorite thing of algebra, of factoring everything. We get 16, x plus 1, x minus 1. And remember, when you set every factor equal to 0, that includes that front factor, but there's no x's there, so we don't really have to worry about that one. We set this equal to 0, so we end up getting -1, and of course you set the other one equal to 0, you get +1. These are my critical values. Okay, but go back to your domain. Since -1 is not in the domain, I'm not worrying about that. I'm only worrying about the +1. Okay, so if I evaluate my function at 1, in the original function, I end up with 7 minus 16 minus 16. Looks like it's a -25. So that has the potential to be a maximum or a minimum. I'll go with that second derivative test that we talked about. Well, what's my second derivative? Well, let's take the first derivative first, right here. And the second derivative looks like it's -32x to the -3. -32 over x cubed. And what I'm doing is I'm plugging in the critical value that we found. This one right here, this +1. And I'm just checking the concavity, and it's negative. So that means we're concave down, and therefore this is a local maximum right here. Okay? So I have the potential of this being the highest point is at -25. Remember, the highest point can be a negative. Now, the only thing I have to worry about is there a potential of my graph going up to infinities? Okay? Well, the fact that it's concave down everywhere means I'm probably not going to have that case. This is going to be my maximum. But show you what else I just want you to consider. Okay, now I know that's the case because it's always concave down. And if it was going to turn around, so we have that point, remember, 1 comma negative 25. So we're talking, it's way down here somewhere. 1 negative 25. Okay, but what we know is it's concave down. We're only worrying about the left side, but is it always concave down? Well, remember, if it was going to turn up, for example, and maybe go like this, there would be a concave up section, and most importantly, there would be another critical value here. We only found critical values at 1 and negative 1, so this shouldn't happen. But regardless, what I'm considering, and I don't even have to write this, I just want to show you all what I'm considering. What happens as you come to 0 from the right side? And what happens the end behavior? Remember that whole thing we learned about what's the derivative as you go, or sorry, what's the limit as you go toward infinity? So look at this function right here. As I approach 0, okay, as I plug in a number very small like 0.001, this becomes a very small number. This goes to 0. This right here is going to infinity because it's a 0 on the bottom. And because it's a positive number I'm plugging in, and because it's a negative there, it's actually going to negative infinity. So it sort of confirms what I thought. That's going to negative infinity. This one right here, what's happening as we go out to the right? So just think of my function. I want to plug in a really big number. Well, as you plug in really big numbers, that means you get a negative 16 over infinity. That's going to 0. And a really big number times 16, negative 16, means it's also going to negative infinity. Okay, like I said, you didn't have to write any of this. It's just me trying to show you what I'm thinking here, but just play around a little bit. Plug in positive 200, plug in 100, plug in 1,000, just to confirm what's going on as you go far to the right, and then plug in a number really close to 0 on the right side, like 0.001, just to confirm that we're not getting any kind of drastic turns, and making sure this is like a downward parabola, and we are in fact having an absolute maximum right there. So that local maximum turns out to be the actual maximum, and that's it for this problem. Okay, now once again, I'm just going to graph it for fun, just to show you, another resource, especially when you're doing your homework. If you're uneasy of it, don't be afraid to just plug this thing in there and see the picture. Now you notice I'm not seeing any picture. Oh, that's fine. Minus. Now this is what we have. Doesn't look like much. It's basically like that last problem, but very extreme. Here's that max that we had, and every point is confirmed going down. Now some of you are going to say, well, what about all these points over here? True, but we're only looking at it from 0 to infinity. So all from the right side, that sure enough is the absolute max. Okay, so I think, let me see, we might have one or two more of these. Let's look at number 27 just to make sure that's still in section 4.5. Yeah, okay. So now we get this function, f of x equals 6x minus 3x natural log of x. Well, they want us to find it only from 0 to infinity, and that happens to be the domain anyway, because remember, you can't get anything 0 or negative inside a natural log. So let's do our same process. Let's find the derivative. Now remember, as you do this derivative over here, we have to do our product rule. Those are what I'm going to take the derivatives of. So I leave the negative 3x. I multiply the derivative of natural log x, which is 1 over x. Then I take the natural log and multiply it by the derivative of negative 3x. That's negative 3. And let me clean this up a little bit so you can see exactly what we're working with. We have 6 minus 3 natural log of x. So that's 3 minus 3 natural log of x. All right, now we set this thing equal to 0. And we're going to see what we end up with. Let's move over here. We get 3 natural log of x equals 3. natural log of x equals 1. And you got to remember, what is it that we're looking for when we get natural log of x equals 1? This is log base e of x. So the question is, what value, if I rewrite this, not even what value here, it's even simple. What it's asking is, what power do you put on the 1 to give you an x? Well, if I switch forms, all it's saying is e to the first equals x. So e equals x. This is my critical value. And remember, e is like 2.7, so it is in between 0 and infinity. Well, let me do that other step that I did before. Let's find the second derivative. I can go and I could test the region around e in the first derivative. If you want, you can still do that to see increasing, decreasing, all that good stuff. I'm just exploring that new rule that we learned. Find the second derivative, and that one's fairly easy. It's just -3 over x. So I plug in e there, which is 2.7. Doesn't really matter what the value is. All I care about is it's negative, so it's concave down. Meaning this is a max, a local max. Okay, so our last part is we want to check and just see. This thing's concave down. I didn't have any other critical points, so it should not be turning around. We shouldn't have a drastic change upward to give me more, higher points. I'm hoping that E is the highest point. Not sure yet, but again, what I want you to consider is what happens as you get close to 0? What happens as you get close to positive infinity, just to see what's going on here. And a couple things. Let's see here. Let's look at, okay, we have the E. Let's plug in the E just to see what we get. So that's going to be 6e minus 3e natural log of e. And just so we're clear, the natural log of e is 1. So f of e is ending up to be 3e. That's our coordinates. And I can't say it enough. E is the number 2.7. So those are like 2.7 comma 8.1 or whatever that might be. That's the actual coordinate. So the only question is that the absolute maximum? All right, so we have the point that looks like it's right around here. We knew it was concave down in that area. We just don't know what happens over here, what happens over here. Well, like I said earlier, if it was going to turn upward, that's the only thing that would mess up my idea of this being the absolute maximum. If it was, though, we would have a critical value down there, so it should not be turning upward. Maybe the concavity will change, but it should not be turning upward. Same thing right here. If they were to turn upward, we would have found another critical point. So I'm safe to say that this is my absolute maximum. Remember, the y value is what they asked for first, and where is it? That's what we have right there. And what I missed? Make sure I plugged in everything right. Okay, my only guess is these are the exact answers. They actually said to round to 2 decimal places, so I'm going to get my calculator out. Let's just see what 3 times e is. So remember, e to the first. So my calculator, I push the power, then I push e button, and it gives me the power. If I went 2 decimal places, I'd be at 2.72. So let me try that. And then if I found e to the third, remember you just hit it, on my calculator, you hit a 3, then you hit that e button, and you get 20 point, sorry, no, not power of 3, sorry, it's e to the third. E right there, times 3 is what I meant to do. So 8.16 is what we get. Let's try plugging those in. Usually you prefer that answer, but, oh, what do they not like in here? 2 decimal places. Oh, I'm sorry, I rounded wrong. Should be 8.15. This is going to be my 3rd try, then we're going to be done. And finally we got it. So, like I said, in a typical calc class, they're going to want you to leave it as E and 3E. In this particular one, more practical, of course. We want to go, they're going to a decimal. It's rounded, so just round those out, and that's what we get. Okay, so sorry about that little delay. Let's look at number 31, if that's part of this section as well. Yeah. Describe the graph of f at the given point relative to the existence of a local max or min. Assume that f of x is continuous, and they tell us a few things. Okay, so this is just to kind of make sure you understand the theorem. You have a point, 2 comma f of 2. Okay, you don't know what that is, but it's the y value of 2. They tell you that f prime of 2 is 0. So right there, what that means is this is critical. It might be a local max. It might be a local min. Okay, more information needs to be told to us. Okay, so that's where we go to the second part here. Then they tell us that the second derivative at 2 is greater than 0. That means it's a positive number, so it's concave up right there. So going back up here, if it's concave up, that means you have a local minimum right there. Okay, so you definitely know it's a local minimum. And can't say it's neither, can't say it's it's definitely not a local max. Unable to determine, not enough. They didn't notice they're not talking about any absolute max or mins. They just want to know about local max or min. So that's all we know right there. That's all we need to know for that number 31. Okay. Okay, so number 35 is going to get us into that section 6 that we're going to do next time. And you're going to see here, this is 35. There's only going to be a couple of problems I'm going to need to do for our next one. It's going to be mainly concepts and just a little bit of work. But for the most part now, you should be able to get through 1 through 34 based on this lecture. And then we'll have a shorter one next time at the end, second half of this week. And then we'll have our spring break. And then the week after, we're going to have section just 5.1. So it's going to be kind of an easy week back from spring break. So hopefully this won't be too much for you all. So work on these. If you have any questions, shoot me an email. But you should be good to go, like I said, through those first handful of problems here. Okay, so that's it. Well, look for the next video. And don't forget to do your quiz due on Monday. Take care.